When a fisherman casts a crankbait and winds it back to the boat, the lure rips through the water. The tackle industry suggests this rapid motion drags a massive, expanding scent cloud right to the hook. This promise of a guaranteed strike is one of the oldest marketing tactics on the shelf. You buy the bait, you buy the gel, and you supposedly leave an irresistible trail. But that assumes water acts like air. In the air, an odor easily drifts and expands. Water, however, is nearly 800 times denser than air and highly viscous. It pushes back. At a chemical level, fish don't smell oils or fats. They detect water-soluble molecules, specifically amino acids, that dissolve into the surrounding medium. Applying those water-soluble scents to a fast-moving bait ignores the unforgiving laws of fluid dynamics. The physics of water actively prevent that scent cloud from ever reaching the fish. This schematic illustrates what engineers call the hydrodynamic boundary layer. Notice the dashed line wrapping around the object. As a lure moves, it disturbs the fluid directly adjacent to it, creating a distinct zone of slowed water. Look closely at the text here defining the no-slip condition. The water molecules touching the lure's surface stick to it, moving at zero velocity relative to the bait. The fluid layers just above that are slowed down, creating a severe velocity gradient. That severe gradient generates intense fluid friction. As the lure is cranked forward, this friction acts as a violent shear force, physically ripping the applied amino acids off the bait's surface in mid-retrieve. The result is a phenomenon known as negative polarity. The scent trail doesn't follow the lure, it expands in the turbulent wake, pointing directly away from the bait's trajectory. Because the lure travels significantly faster than those molecules can diffuse through the water, the bait is washed chemically clean within seconds of splashdown. The high-speed retrieve deposits the scent molecules yards behind the actual location of the hook. A predator might detect the trail, but following it leads them to an empty stretch of water. Now look at the predator waiting in the shadows. The anatomy of a fish's snout is highly evolved to intercept microscopic chemical cues in still or gently flowing water. Inside the nasal cavity sits the olfactory rosette. Its multilamellar folds maximize the sensory surface area within a highly confined anatomical space. Fish don't passively wait for scents to wash over this tissue. They actively pump water through the cavity, using rhythmic mechanical agitation of their accessory nasal sacs to sniff the surrounding environment. This system is extraordinarily sensitive. Research shows fish can detect a single target amino acid molecule suspended among a billion water molecules. This creates a severe disconnect. The fish is a biological marvel built to identify incredibly faint traces, but it cannot track a target if fluid dynamics have already washed the chemical evidence downstream. To see how scent works, we have to look at a stationary environment. Consider a scent-impregnated plastic bait resting motionless on a lake bed. Without the violent shear forces of a high-speed retrieve, the boundary layer disappears. A completely different physical process takes over: molecular diffusion. This graph charts how specific diffusion coefficients dictate the speed at which this happens. Amino acids slowly and steadily radiate outward from the bait into the surrounding water. This slow radiation builds a dense, stable chemical space. It expands outward in all directions, acting as an invisible beacon in the dark. This unbroken gradient is the exact environmental condition a fish's olfactory system spent millions of years evolving to exploit. When a predator approaches, it enters the outer edges of this stable gradient. The scent space is highly concentrated and physically intact. As the fish draws near, its accessory sacs pump the concentrated scent trail directly over the olfactory rosette. Those target amino acid molecules lock into the receptors, triggering the recognition wiring in the brain. The dinner bell rings, and the fish initiates targeted food-seeking behavior directly at the stationary bait. Artificial scents are physically incompatible with speed. Ripping a bait through the water destroys the chemical signal. These attractants are biological triggers.